Okay, so for section 2.1, we're going to be discussing inductive reasoning and conjecture. For the first example, before we've even defined anything, all it's asking for us to do is to find the next two terms in the sequence. So basically what we need to do is we need to notice what's going on and try to come up with a guess as to what's going to happen next. So it starts with 384, then 192, then 96, then 48. Hopefully you've started to notice that the numbers are getting smaller. After investigating a little bit further, perhaps you start to notice that the numbers are being cut in half, which then leads us to the prediction that the next number in the sequence would be 48 divided by 2, which is 24, and 24 divided by 2, which is 12. What we just used is inductive reasoning. This is where we reached a conclusion based off of the pattern that we noticed. We made an educated guess or a conjecture about what was going to come next. So our conclusion was that by cutting the numbers in half, we could find out the numbers that were missing. So in example 2, we're going to make a conjecture or an educated guess about the sum of the cubes of the first 25 counting numbers. Now, I don't want to sit here and cube the first 25 counting numbers, so hopefully there's a pattern that develops that will make it a little bit easier on us. If you notice, the first part says that 1 cubed is equal to 1, which can be rewritten as the square of 1, which is 1 squared. This really hasn't done much for us. Let's look at the second line. 1 cubed plus 2 cubed is equal to 9, which is the same thing as 3 cubed, which is equal to 1 plus 2 quantity squared. So it's almost like they just took the 1 and the 2, added them together, and squared them, and that's how they got to the 9. Looking at this next line, 1 cubed plus 2 cubed plus 3 cubed is 36, which again, going off of that pattern, the sum of 1, 2, and 3 quantity squared is another way to get to that 36. So it almost looks like instead of cubing them as individuals, we can take their sum and then square that sum in the end. So the conjecture here is that the sum of the first 25 counting numbers cubed, so let me write this out, is going to equal the sum of each of those counting numbers added together first, and then you take that quantity and square it. So what we did is we observed a pattern and we made a prediction. We're going to look at testing our conjectures in example 3. This is saying that the first odd prime numbers are 3, 5, and 7. So what we're going to do is we're going to make a conjecture about the next odd prime number. So let's go ahead and look at the pattern that's going on with the numbers that they gave us. From 3 to 5, what is the change? Same thing with 5 to 7. What change is occurring here between these first two and these second two? Hopefully you notice that between 3 and 5 we've gone up by 2, and the same thing between 5 and 7. So my conjecture here is that the next odd prime number, let me write that down, the next odd prime number is 9. All I did to get to that is I added 2 from 7. Now my question to you is this a true statement or is this a false statement? You need to think about what it means to be odd, 9 works, and prime. This is where the 9 prediction does not work. 9 is composite, so this is a false answer or a false conjecture because 9 is composite. So our pattern that we observed, unfortunately, broke. The numbers that they gave us led us to one conclusion or one conjecture, when in reality we know that 9 is not an odd number. Instead, 11 is the next odd prime number. The issue with making conjectures is that we are doing our very best to observe our patterns, but sometimes the observations that we make are faulty or the information that we have is not enough. So if we can find what's called a counterexample, that will basically negate a false conjecture. A counterexample is something that makes our conjecture false. So our prediction was that every time you're looking for an odd prime number, you just add 2. The counterexample is 9 because 9 fit that pattern but did not fit the rule. When we're finding counterexamples, these examples are a little bit more difficult. I'm actually going to start on B and then come back to A. So if I look at B, it says, if the name of a state includes the word new, then the state borders an ocean. So hopefully you're thinking about different states in the United States that have the word new in them, like New York or New Jersey. And if you know your geography, New York and New Jersey do in fact border the ocean. We're looking for the state that does not fit this rule. And there's one of them, New Mexico. So New Mexico serves as our counterexample because it basically shows that this rule doesn't work all the time. Looking back here at this example, if x squared is greater than or equal to 0, so basically if you take some number and square it, it's going to be positive or equal to 0, then that means that the original number itself, before being squared, was also going to be positive or equal to 0. So let's test some things here and see if that works. Throwing out some numbers, maybe you've thought of some numbers on your own. A number that usually gets thrown out is, let's try the number 2. So I'm going to go ahead and take 2 and square it. So this is saying that when I take 2 and square it, that should be greater than or equal to 0. So if this half is true, then we can go to the second half. Let's make sure this half is true. 2 squared is 4. 4 is greater than or equal to 0? The answer is yes. So the first part was true, so let's make sure that the second part held true. That means that 2 was greater than or equal to 0. And the answer to that is, well, yes, that's also true. If you throw out a lot of numbers, this is always going to work, except when I say always, it only always works if the numbers themselves started off as 0 or positives. If I throw out a negative number, like -2 quantity squared, let's see what happens. So -2 times -2 is a positive 4. Is 4 greater than or equal to 0? This half is a yes. Going to the second half, that means that my original number, -2, was greater than or equal to 0. And this is a no, which means any negative number is a counterexample. Reason being is because when you take a number and take that quantity and square it, it will result in a positive value, unless the number was 0 to begin with. However, the number that began, if it were negative, it starts off less than 0. In example 5, I want you to think about some things that would be true conjectures and false conjectures based off of the information that you have. We're not looking for you to come up with one right word or one right idea. You're trying to come up with something that when I'm looking at these numbers and these patterns and I try to apply it to any set that I can think of, it will always be true. So I've got 5 times 7 is 35, 5 times 3 is 15, 5 times 11 is 55, and so on. Hopefully, after thinking for a couple minutes, you realize that we're taking an odd number times an odd number, and it's resulting in an odd number. If you take any two odd numbers, 3 times 3, 1 times 253, whatever they may be, an odd times an odd will be an odd. So our conjecture that we know is true is an odd number times another number that is odd will also make an odd product. Now, if that's not the true conjecture that you came up with, that's okay. We're just looking for something that will hold true. Now it wants us to come up with a false conjecture based off of this information. So I see a 5 times something, a 5 times something, a 5 times something. I'm seeing all these are 5 times something, and my ending numbers here are all ending in 5. So my conjecture is that 5 times any number is going to give me a product that ends in 5. Is that true though? Can you think of a counterexample? Hopefully if you do 5 times an even number, like 5 times 4, let me write that out, that will result in 20, which doesn't end in 5. Because that negates my negates my conjecture, that makes it a counterexample. So my false conjecture is 5 times any number is 5, going to end in a 5.